Hey guys, Akil Mohideen here, and welcome back to another video. Today we're going to be continuing on with how CPU cache really works, and we're going to do that by introducing something called the flip-flop, and we're going to learn how we can use the flip-flop to actually store values. So here's the clock circuit that we built previously, and you'll notice that the LED is actually beating much slower than before, and that's because I raised this capacitor up to 10 microfarads. Up to 100 microfarads. It was 10 microfarads previously, now it's 100. And I did this so it approximately makes the beat about 10 times slower. And another way you could do this is by putting a resistor between the capacitor and ground. Because the way a capacitor works is actually, if you look at a symbol for it, I know this is kind of like, off of what we usually talk about, but I hope you guys can see this. But the symbol for a capacitor is usually something along these lines, right? Where they denote, like, say, one of these is positive and the other one is negative, right? Oh no, they do a line, right? That. I've seen it both ways though. I've seen it where people do two things like this, and I've also seen this. I think this is the proper way to do it, that one. So we're gonna go ahead and do this like this. And what this actually stands for is, surprisingly, that's actually exactly what is inside of a capacitor. There's two metal plates. So there's one metal plate here, and there's one metal plate here, and with a little bit of air in between them, okay? And depending on how much air is in between them, and depending on the size of the plates, you actually get the overall capacitance of the capacitor. So what happens is one of these is connected to plus, and one of these is connected to negative. And as positive holes, right? Because remember, electricity is the flow of electrons. So when you have a positive current, that means that you actually have the lack of electrons, right? When you have positive, it actually means the lack of electrons. So as positive holes begin to collect on here, or as electrons begin to leave this plate, we get a positive voltage here, right? And depending on that air that's in between them, it will attract negative voltage upon here. So electrons will start to collect all along this metal piece, okay? Because they're attracted by this positive field, right? And depending on how big this piece of metal is, how big this plate is, you can collect more positive charges on here, or you can collect more negative charges on here. Or if you raise the gap of air in between them, you actually make it this way you need more positive voltage on this plate to attract negative voltage onto this plate as well, right? Because if they're farther apart, the field is not as large, right? If they're farther apart, the field won't be as strong on the other plate. So what they do is here, so that this way a bunch of electrons begin to collect on here, and a bunch of positive holes begin to collect on here. And what you've actually created is that they want to stay here on these plates, which is why sometimes if you take, because they're attracted to each other, right? Which is sometimes when you unplug a capacitor when it's full, like, when you have a computer or something, or like a PSU, and they say, you know what, when you unplug it, if you're going to be working on your PSU or something, you're going to be changing the fan in it or whatever, make sure you unplug the PSU and maybe let it sit overnight. This way you give chance for the electrons to leave the plate, or for the positive holes to also leave the plate. Because they want to stay here. They want to stay here because what you really created is a battery, but a battery that the charge doesn't stay on there for as long. And they stay like this until you connect a piece of wire here, but that's totally not what we're caring about here. What I'm saying is, though, the way you can make it, because what we're doing here in the circuit is we're trying to make it so this way it takes longer for the capacitor to charge up, right? Now you can do that by using a larger capacitor, aka more air in between and larger plates, or you can do that by making it go through a resistor before onto one of the plates. Okay, now it's harder for electrons to flow onto this plate, so it takes longer for the capacitor to charge up, really. And that's effectively what we've done here. So what I did is I got a larger capacitor, but I could have achieved the same thing by just connecting one of the terminals of the capacitor with a resistor. Yeah, so that's sort of what we did. I know that was off topic, but it's kind of a cool thing to understand how each of these components work, I feel like. Now, back to the flip-flop thing. So what we're doing with the flip-flop is we're using the clock to say when we want to set the value. Okay? We're using the clock to say when we want to set the value. So when I press this button, I'm going to hold it this way. You're going to see something that happens. Okay? There you go. And it holds it. Okay? Until the next clock cycle comes. Okay? Until the next clock cycle comes, it holds the value. Right? I have to hold it until the LED comes up. Right? And then it'll stay on forever until the next clock cycle comes and resets it. Now, what you might think is here, oh, each clock cycle it's resetting the value, but actually that's not what it's doing. On each clock cycle, it's saying what's the value here on this. There's a terminal on this IC that is D, stands for data. Okay, and it says what's the value of data. When I press this, I make data high. Okay, so it says when this clock is on, or rather we'll learn about it later, but when this clock transitions from low to high, what is the value of data? And if data is 1, then keep the LED on. But then on the next clock cycle, when it changes from low to high, the LED powers up, it asks what's the value of data, and since my finger's not on it anymore, the value of data is 0. So it changes the value of the flip-flop down to 0, and which is why the LED turns off. So it's not that this is resetting it, it's rather just saying, oh, what's the value of data? And I can achieve the same thing, right? Hold it, and then put my finger back on it, and it'll stay 1, right? If I just keep doing this, it's holding the value, but every single time that the next clock cycle comes, my finger is constantly on data and keeping data 1. The next time I don't do it, it turns off. So this is a really important concept to understand, that really what we're doing now is not using set and reset. And if you look at the actual values of the flip-flop that I have here, the 4013, they do have a set and reset terminals. I don't know if you guys can see that, but they do have set, reset at pin 4 and pin 6 is set and reset. So, but we're not using those anymore. Set and reset I have set to ground, and I have instead used clock and data, which is pins 3 and 5. And this is important because this is a much heavier sought after method. Right? This is a method that is more common in the field of electronics, to use a flip-flop in this way, to do data storage in this way. And you guys can't even see the LED, but I'm unplugging it now. Okay. Now, what we're doing is, if we draw a graph of what of clock, okay, and we have it go like this. Okay, and so it's going on 1, and then here goes to high, and then comes down, and then goes here. Okay, now I realize that all these bumps and the wavelength is not completely uniform, but it would be because it's the clock. It would be all uniform. Let's just imagine that it's uniform here. Okay, so next we have data. Okay, now data is just short for D. Okay, and then we'll have Q, which is the output. Now you'll notice I didn't plug in an LED to Q opposite of Q because it's just kind of annoying. Let's say D. Okay, so now let's say I started off by I press the button for this long, and then I let go, and then I didn't press the button for a while until about halfway into this clock cycle, and then I just press the button again. Okay, now let's check out what this output would be. So what you do is on this rise, my hand blocking it? No, okay. On this rise, this thing right here, you detect when the voltage changes from low to high. Not for how long is it high or how long is it low, rather you detect when does it change from low to high, and you do that with something called an edge detector. And I'll teach you guys how to make an edge detector later. It's the simplest circuit you guys have ever seen, but it's a good circuit, okay, and vital to the flip-flop. So what you're doing is clock and D, you're saying when it changes from low to high, what's the value of D? So you can go ahead and drag this down, and the value of D when it changes from low to high, so Q automatically starts off at 0, right? But as soon as it hits this edge, it says what's the value of D when the clock cycle changes from low to high, okay? And it's 1. Okay, then go to the next edge, okay, when we're drawing the graph. this is the next edge when it changes from low to high, right? This thing. What's the value of D here? This is low, right here. So it's down here, okay? So now it's going to be high for all this time until the next clock cycle, and then it'll change down to low, okay? Now, this is important, okay? So it stays high for all this time, and even though I let go of D in the middle of a clock cycle, it doesn't care, because as whatever the value of the clock cycle, whatever the value of D is when the clock cycle changes from low to high, is the value of Q until the next clock cycle sets what D will be again. Until the next clock cycle sets what Q will be again. Okay? So here we've reset Q. We've set Q back to 0 because D was low when the clock cycle changed from low to high. Okay? Now on the next clock cycle, and it'll continue to stay low until here, until the next clock cycle. Okay? This is the next time it changes from low to high. What's the value at D here? It's 0. Okay? So it's going to continue on being 0 until the next clock cycle, which is here. Okay, the next clock cycle is right here, change from low to high. What's the value of D? It's 1. So then here, it'll change to 1, and it'll just continue to do so until the next clock cycle. So this is the actual value of Q that we have here. Okay? And this is what's so interesting about the flip-flop, that it's a lot more different. And you might ask, well then what happened to set and reset if we're doing clock cycle and D? Now, the difference is that what you're doing is that if D is low, reset. If D is high, when it changes from, this is all assuming that on the clock cycle when it changes from low to high, right? On the clock cycle when it changes from low to high, if D is low, do reset. If D is high, then do set. So we're still using the same thing, but just in a different way. We're having the IC take care of it. And you can build this manually, right? Because on the flip-flop, they still have a set and reset. Like I said, this is the data sheet for a flip-flop. They still have set and reset. So you can do it yourself. You can build the inner workings of a flip-flop yourself with a flip-flop if you really want to, just not using all the enhancements that a flip-flop automatically comes with. But since they already come with all these, abilities, all this stuff that it automatically does for you, this is why we use it, okay? And this is good because now we only have to care about this. And more importantly, you can really save power with a flip-flop. And I'll tell you why, okay? Now usually for a clock, you can do it in a way that the length at which the LED is on is equal to the length of time that the LED is off, which is usually what's so great about the clock, right? It's constantly on, constantly off, and very uniform time schedule, right? But what we actually do is we only care about this little bump. We only care about when it changes from low to high. So we really only care about this small section, right? All we care is about when it changes from low to high. And right after that happens, right after this low to high happens, we can just make it go immediately down to low again. Because who cares, right? And then we can have it be low for a long time, and then just change it really fast again. And have it be low, and change it really fast again, right? So we don't have to have all this power for this entire time. We can have it really short. We can have it even shorter than this. Right? I'm just drawing it like this way you can actually see it. We can have it so tiny. It only needs to be about 2 or 3 nanoseconds that the power needs to be on for the flip-flop to detect it, and then power can be cut off. No one cares. Pins 4 and 6, I believe. Okay, 4 and 6. I already said, 4 and 6, I already said, go straight to ground. Okay? Because those are the set and the reset, and we don't really care about those ones. Okay, set and reset automatically go to ground. The 5 is the data though. Okay, and the 5 is going to our 5 volts. The 5th pin, let me draw that. The 5th pin is going to 5 volts. Okay, obviously with the pull down resistor. I should not have to keep drawing these things. You guys should know that by now. But with a pull-down resistor, obviously, and it goes to 5. And then 3 is the clock. And the clock goes to our little clock circuit that we built earlier. Remember this? This clock circuit that we built last time? Yeah. This is going to go to the clock circuit. So you can see how components are starting to come together now. But this is going to go towards the clock. And then 1, this is 3. 1 is our output. And then 2, I believe, is inverse of Q, but who cares? And then obviously 7 goes to ground and 14 goes to power. And in this flip-flop, I actually have 2 flip-flops inside. So I can hold 2 bits, right? Because each of these Qs is only 1 bit. So what we need is, first of all, there's 2 in them, right? So if we want to hold an 8-bit number, this is going to be equal to, I'm going to say this is just equal to a block, right? This whole thing is equal to a block, and each block holds 2 bits, right? Each block holds 2 bits because there's 1 bit on this side and 1 bit of this on this side of the IC. So now, what we need is, if say we want to have, I don't know how much RAM you guys want to have. Let's not make it too much. We're not going to make this like a 4 GB system because that's stupid. And you guys can also see when you start programming the CPU, you can see how little RAM you actually need to accomplish so much, right? Like your games and stuff, like on your PC you might have like 4 GB of RAM. On your phone you probably have like 2 or 3 GB of RAM, right? But on your computer you might have 4 if your computer's a little older, or you might even have 8 or 16 or something, right? A lot of RAM. But for us, we are going to be in megabytes of RAM. Or sorry, not even megabytes. We're going to be in bytes of RAM. Probably 16 bytes of RAM. Which is nothing. But it's going to be so hard to build. Because RAM takes up a lot of space here. At least for us. How small they make RAM in actual computers, I don't actually know how small they can make RAM. Like in comparison, like how small they can make the rest of the components. But for us, RAM is going to be taking up a huge amount of space, because for an entire flip-flop IC, we can only accomplish 2 bits. Now I'm sure they sell ICs that probably can hold 4 bits in a single IC, but that's not for us. That's just because I already had 50 flip-flops lying around, so we're just going to end up using those. But for like our ALU, we can get that done in 1 IC. Although, you know, you could expand that out to the entire board like we had before. Not important though. Space is not really an issue for us. So what we're going to do is we have these blocks. So each block is equal to 2 bits. So we're going to need to have 4 of them. And this is going to be equal to 1 byte. Right? So this is going to be equal to a single number. 1 byte for flip-flop IC is going to be equal to a single number. And if we want to do anything, add, subtract, divide, whatever, you're going to need more than 1 byte. You're going to need 3 bytes minimum just to do some simple calculation, right? Because you need 1 for A, you need 1 for B, and you need 1 for C. So what we're gonna do is I'm gonna abbreviate this to triangle now. Okay. 4 flip-flops is equal to 1 byte, which is going to be abbreviated as a triangle. Now, you only need 3 bytes to really do any simple calculation, like add, subtract. You only need 3 bytes. You need A, B, and C. Now, if that's all we wanted to do, that's fine. But, you know, we're building this. If we want to do a more complicated program or something, we could probably put like 8 bytes in here or something, or even 16. And 16 bytes is a lot of RAM. You know, it doesn't sound like a lot of RAM because your computer probably has like 8 or so, but it's quite a bit. Right? And that just gives you an idea of how many variables that your computer is holding. Because remember, CPU cache and RAM, all they do is just hold variables that need to be accessed by the CPU. So you can imagine if you have it like, if 4 GB of RAM is bottlenecking your system, imagine how many variables the OS and your game and your YouTube or whatever Facebook is open is just how much variables there are in that system, in that program. So for us, we're probably only going to need a minimum of 3 bytes, right? So like plus, right, triangle plus triangle equals triangle, so you're going to need 3 bytes, A, B, C, but we could probably do like 8 triangles, right? although this is kind of stupid to draw out, but we could do like 8 triangles, 8 bytes, if we wanted to. We could even do 16 or 32. And we'll talk more about this later in CPU architecture, and it's a really, really good topic to understand. But other than that, I think this pretty much wraps up this video, guys. Other than that, I think I'll just see you guys in the next one.